Welcome. This video is a short demonstration showing the ECS example project user interface in action while running a 4-cylinder GDI engine. Before we start the engine, we must enable sync, which tells the FPGA to begin tracking engine position and in turn enables all engine synchronous functions such as fuel injection and spark ignition. As we crank the engine, we begin to see set point and actuator responses on the large trend chart in the center of the screen. The faults subhost displays a list of active faults and controls for various fault thresholds. This user interface is the included host VI for the ECS example. It acts as a showcase of the many useful features that can be built into a LabVIEW-based user interface or UI. On the right-hand side of the screen, an engine load versus speed plot is shown above a return map. The return map displays a visual representation of stability by plotting the last n samples of a selected parameter in an I versus I-1 format. The ECS example real-time software is abstracted into 3 layers: hardware, engine, and control. The user interface subhosts are organized in a similar fashion. Subhosts, or secondary user interface VIs, can be opened by double-clicking an item on the subhost list or single-clicking on a subhost icon. The load command subhost contains controls and indicators relevant to manipulating the desired torque. In a torque-based engine controller, the desired torque is a primary input to most engine functions. 2 important subfunctions of the load command are the low and high speed governors, each of which has its own subhost. Both low and high-speed governors, as well as many other functions within the ECS example, have PID constants which must be tuned in order to function properly. As the pedal position is increased, engine speed also increases given zero load on the driveshaft. As the engine speed approaches the high idle set point of 2500 RPM, the high idle governor takes priority over the manual pedal input. Manual control of nearly every set point is available throughout the ECS example. The fuel command subhost contains controls and indicators relevant to manipulating the desired fuel output. In a fuel follows air type engine controller, desired fuel is calculated by adding a feed-forward value of fuel based on the mass of intake air and a feedback value based on lambda measured in the exhaust. In an air follows fuel type engine controller, desired torque is often converted directly into a desired fuel quantity. Other fuel control strategies, such as overspeed fuel cut or a smoke limiter, are also implemented in the fuel command subhost. By setting the overspeed fuel cut max engine speed control to 2000 RPM and the re-engage speed to 1900 RPM, we can expect the engine speed to fluctuate between 2000 and 1900 RPM once the fuel cut condition is met, which in this case means the engine speed has exceeded 2000 RPM. Subhosts under the engine subhost list are primarily geared toward configuring sensors and actuators that are specific to the engine under test. The DI setup subhost contains the injector calibration table, which relates a desired volume of fuel per injection into an injection duration or pulse width. Other controls include manual injection durations, pilot, main, and post injection enable-disable switches, min and max injection durations, and injection windows. The medium pressure common rail setup subhost contains controls relevant to engine synchronous solenoid pump rail pressure control. The rail pressure control set point is set on the rail pressure control subhost under the control subhost list. Subhosts under the control subhost list are primarily geared toward combustion or control algorithms. As the rail pressure set point is manipulated manually, the trend chart on the main host window shows rail pressure tracking closely with the target set point. The intake air measured subhost allows for several modes of operation. This engine utilizes a map sensor with no EGR, which only requires a simple volumetric efficiency, or VE, lookup table to calculate intake air mass flow. The VE table has the ability to learn over time based on lambda feedback from the exhaust. The intake air desired subhost contains controls which manipulate the intake air mass flow and pressure set points. Controlling intake air mass flow to a desired set point using a drive-by-wire throttle is a complex task. Often an open-loop lookup table is used for this purpose, or the pedal position is used directly to set the throttle position. The suite of sensors on a given engine is commonly unique to that engine. As a result, sensor calibrations must be known and entered into the sensor's setup in the engine layer. This includes pressure transducer voltage to pressure calibrations and thermistor resistance to temperature calibrations. Spark ignition parameters are configured on the spark control subhost. Spark advance or timing is set with the base advance lookup table and is further modified by various subsequent lookup tables. Spark dwell is set from a lookup table which is based on battery voltage. Spark timing and dwell can be manipulated manually by switching the manual enable parameter to true and setting the manual value. Direct injection strategies are often a primary focus of engine research. Direct injection control parameters such as timing and duration are available for up to 5 injections per cylinder per cycle. Next cycle feedback control, an advanced feature, is available when ECS is coupled with the NI combustion analysis software, or NI CAS. Since engine cranking often requires very different control strategies than typical operation, the ECS code enables a separate cranking state with unique calculations and lookup tables for various parameters which are used during the cranking period. With wideband O2 or UAGO sensor feedback, the ECS software is able to tightly control a targeted lambda or air-fuel ratio set point. To demonstrate or test the closed-loop PID parameters, a periodic oscillation can be superimposed on the lambda set point. Subhosts under the hardware subhost list are primarily geared toward configuring NI C-RIO modules and FPGA tasks such as EPT. Each DI driver setup window contains controls and indicators specific to each NI 9751 module in the ECS hardware platform. This window is where the injector voltage and current profiles are set for all injectors driven from the currently selected DI module. The 80 combo module analog and digital channels are configured on the NI 9752 setup subhost. Pull up, pull down, or divide resistor values for the analog inputs and digital input filter values can be set on a channel-to-channel basis. The NI 9759 throttle setup subhost contains parameters for throttle position and control calibration. The NI 9759 Rev B2 device driver is capable of automatic position calibration but requires manual control calibration. The NI 9757 O2 setup subhost displays sensor status information. Many additional features not shown in this video are available in the ECS example software. To download the NI ECS example project for LabVIEW 2014 for free, visit ni.com, register for a free user account, and search for the ECS example project.